Authored by veteran chemistry teacher Abdul Shakur, these two textbooks provide all the essentials that would not only enable students to master grade 11 chemistry, but to excel at the next higher level in this subject. What make these texts unique are their creativity and profundity with which concepts are explained for clarity and mastery. The following is one of a set of 44 different tutorials created by the author, using materials primarily from the text Chemistry 11 in Focus. I hope you enjoyed this video. If you liked it, please give it a thumbs up and don't forget to subscribe. We will see you in the next video and thank you for watching.
Today our lesson continues with single displacement reactions. We'll see how single displacement reaction can be used to develop a mini reactivity series for a few metallic elements. Recall from video 11, the previous video, that when magnesium reacts with a solution of copper 2 sulfate, the blue solution was changed to colorless and a precipitate of copper was formed. In that case, magnesium, being more reactive than copper, was able to displace it from an aqueous solution of one of its salts. In this case was copper 2 sulfate. So this was the reaction here. This magnesium here, being more reactive and copper in this solution here, was able to displace it there. Now, the same reaction here is demonstrated in this figure here. Here we're having again a test tube with a sample of copper 2 sulfate solution, and this is your strip of magnesium. If I dip that inside a solution here, you can see that a coating of copper is being formed on the magnesium strip. So when you remove that, you can see the copper being deposited there. If you left this inside here overnight, of course, you'll get what you had yesterday. The solution is going to go colorless, and the copper that was deposited on top here will fall to the bottom. In this case, we just want to see whether or not the strip here is more reactive than that. So we put it inside for a few seconds, and we take it out. So this is what we'll do. If we want to know if an element is more reactive than another element, in this case, we wanted to know if magnesium was more reactive than copper. We take a strip of that element, which in this case is magnesium, and we get an aqueous salt solution of the other one, and we dip the metal strip inside, remove it and absorb. If a coating is formed on the strip that you're testing, it means that this metallic strip here is more reactive than the metal from which this aqueous solution was formed, in this case is copper. So this is the observation that we're going to make when we do the next activity that we're trying to do here now. So this is the deal then. To know if one metal is more reactive than another, a strip of that metal is dipped into an aqueous salt solution of the other metal, and observation is made. If a coating is formed on top of a strip being dipped, it is more reactive than the other one. If not, it is less reactive. So what we have here is this. We do not know how reactive these guys are. We have 7 different strips of elements here. You have a strip magnesium, aluminum strip, zinc, tin, iron, copper, and lead. These are metallic strips that we have. So we want to determine which is most reactive and which is least reactive, and then we rank them according to their relative reactivity. For material A, you use eye protection, aprons, you have all these strips, and we get salt solutions of all of these here. So you get a salt solution of magnesium in the form of magnesium nitrate, aluminum nitrate, iron 3 nitrate, tin 2 nitrate, zinc nitrate, lead 2 nitrate, and copper 2 nitrate. You make solutions of these. We have 7 of these beakers here. So we label each of these with the names of the solution provided. So this is what we have here. We're going to have all these labels there, copper 2 nitrate, all see their label there. All these beakers are labeled. So I'm going to get now 50 milliliters of each of these solutions from their stock solutions and put them into each of these here. That's good. We have these 7 strips. You take each one of them separately. In this case, we start with copper, and you dip it into each of these. So in this case, we dip it in the copper, absorb the tip there that's dipped inside, if there's a coating form or not, wash it out, wipe it, and repeat this process for the rest of the solutions while making observations of the tip of the strip of the copper that was inserted in each solution. Repeat this whole set of tests for each of the other metal strips separately with the solutions and make recordings of the observations. Wherever there is a check mark, it means that this metal here is more reactive than the one from which this aqueous solution was made. So magnesium here apparently is more reactive than copper, or we know that. Of course, an element will not displace its own self. You see, it displaces aluminum, it displaces iron, it displaces tin, it displaces zinc, and it displaces lead. So you have 5 check marks. Aluminum now is able to do copper, not magnesium, not itself. It's able to displace iron, tin, zinc, and lead. Iron now is able to displace copper, not aluminum, not magnesium, not iron, tin, not zinc, and lead. Zinc, see zinc? Zinc is able to displace copper, say check mark here, not magnesium, not aluminum, iron yes, tin yes, not itself, and lead. Okay? Alright, and I have tin now. Tin is able to do copper, none of those there, and lead here. And of course, lead is only able to do copper there. I see your chest in memory here, none of the others. And your friend copper now is not able to displace anything there. So how you think we'll know which is the most reactive one? What do you do? The check marks. See which one has the highest tally of check marks. But that one is able to displace most of them. So now, there's an analysis here. Magnesium is able to displace all elements from their aqueous solution. Be able to displace all. Aluminum is able to displace all except magnesium. Zinc is able to displace all except these two here. Okay. Iron is able to displace all. A few of them except these, and copper was not able. So how would you rank these? I would say based on that, magnesium will be in front, followed by aluminum, followed by zinc, followed by iron, followed by lead. What did copper do? Copper was not able to displace anything. So this is how it's going to be. Alright? So if you want to create a mini activity series, this is going to be. This one will be the most reactive, and this one is going to be least reactive. Let's say you did not have this here, this reactivity series that has been created by scientists. You could use that same single displacement reaction there with these metals here and their aqueous salt solutions to create a mini activity series. But this is the one that has been developed by scientists already. Lithium, potassium, barium, calcium, sodium, magnesium, aluminum, chromium, zinc, iron, cadmium, cobalt, nickel, tin, lead, hydrogen, copper, silver, and gold. These metals here can displace hydrogen from cold water. Cold water means water at ordinary temperature. These will only be able to displace metals from dilute acid. That's the only way you get hydrogen into. But these are very reactive. That's why they can displace hydrogen from water. These not being so reactive can only displace the hydrogen from dilute acids. Okay, so that was developing a mini activity series for a few metal strips. If you want to develop a mini reactivity series with these airlines here, these are the materials that you use. High protection, you have 16 10 milliliter test tube. You'll have aqueous solution of these. Although we're not using metal strips now, you'll have gaseous sources of these. They're called halogens: fluorine, chlorine, bromine, and iodine. Just like how we did it last time, right? You're going to get solutions of these, and in each of these, you'll pass these gases inside. And you look to see where a change takes place. Okay? So that's what we have there. You have 4 of these with the halides inside. And you take 2 milliliter samples of each. Okay, label test tube. And put each of these inside the respective test tube that has their name. And you bubble now these gases separately into each of them. and record that. Of course, the cleanup being done. So this is what we have here. All right. Took me a long time to do this. Let's digest this a little bit. Here is sodium fluoride, an aqueous solution of sodium fluoride. This is an aqueous solution of potassium chloride. And this is an aqueous solution of sodium bromide. And this is an aqueous solution of potassium iodide. So what we'll do now, we'll take this gas here, fluorine gas from a source, and we'll pass it through sodium fluoride, and they pass it through potassium chloride, sodium bromide, potassium iodide there, and you observe. Now this is what happened here. No reaction took place because you see the solution stays the same. If you pass fluorine through chloride now, look, you get a change of color. That change of color happens because fluorine is able to displace the chlorine here, and the chlorine comes out as a gas, and it dissolves inside there a little bit, and it imparts that color to the solution. So whenever we see a color change, that's indicative of a displacement that is happening. Look now, this is sodium bromide. You get a color here because the fluorine being more reactive than bromine produces bromine vapor, and the bromine vapor here creates that color there. Same thing is happening with iodine here. Fluorine, okay, displaces iodine, and you get iodine being formed there, and it has a darker color in this case. So in this case, you can see, you can make a judgment right now, that fluorine is more reactive than chlorine, is more reactive than bromine, and more reactive than iodine, because it was able to displace each of those in the solutions. Now we're going to try out these with chlorine now. Pass chlorine into each of these here, all right? So this is what it was before, sodium fluoride, no change, stays the same. Chlorine in the chloride here, no change, it wouldn't displace its own self. But look what happens. Chlorine displaces bromine according to this reaction here, and it also displaces iodine here according to that reaction here. So we say is able to displace bromine and iodine. Therefore we can say, safely say, chlorine is more reactive than bromine and iodine. So now we're going to use bromine gas now. So bromine here. Bromine is a reddish brown vapor. We bubble it through sodium fluoride. See, nothing happens there. Potassium chloride, nothing happens there. It wouldn't displace its own self, but look, is able to displace iodine because of the color change. Okay, that's potassium iodide. You get the color change. Of course, bromine, iodine will not be able to displace anything. Everything stays the same. Okay? So I hope that was useful to you. So now you look at how you displace this. Fluorine was able to displace all of these from the metal halides. Chlorine was able to displace these, and not fluorine. Bromine was only able to displace iodine, and not those. Iodine wasn't able to displace anything. So this is going to be your mini reactivity series there for the halogens. Fluorine is more reactive than chlorine, and bromine than iodine, okay? We did this reaction already. I just put this here for you to see. Remember I told you when very reactive elements such as potassium reacts with water, this one here, you get a flame being produced. You see that? It burns the hydrogen that's formed, it burns spontaneously. Okay? And I give you all this reaction there yesterday to show you how it is a potassium ion that's forcing its electron onto this hydrogen here. That's where you get hydrogen gas here. We also want to show water is electrolyzed. These two test tubes are filled with water and then inverted over these electrodes here, which are immersed in water from the trough. The current is then turned on and observations are made. You will see bubbles coming up here. As the bubble goes up, it displaces the water downwards. So you can see that twice the volume of hydrogen is being produced here than the volume of oxygen. Let's see why that is so. Now, water ionizes like this. You have four H's and four OH's, right? The hydrogen now picks up electrons from the cathode here. The cathode is what is providing electron now, and you get two molecules, or we can say 2 moles of hydrogen, right? And here 4 of these are given off 4 electrons. When you do electrolysis, it's called electrolysis. The number of electrons produced by the cathode will be equal to the number of electrons accepted by the anode. So you're getting that now, same number of electrons on both sides. Now look what happens. You get 2 hydrogens here and 1 oxygen. So in this case, you do gas laws later on. Here you have 2 volumes here to 1 volume here. And of course, we spoke about this concentration that's so low yesterday, okay? So that's electrolysis of water there. What else? On here are some questions for you to do. You have to balance those single displacement reaction. Again, you balance that. Complete and balance. You have to use the reactivity series to determine whether or not these are going to react. You know how to do that. The one that is lower down will not be able to display, but for the metals that are higher up in the reactivity series, they're able to displace those at the bottom there. So you get a reactivity series, and whichever metal is above another one, you'll be able to displace that metal from an aqueous solution with salt. So you can do that. The answers are all. These problems are restated in the solution manual, and you can see the result there. It's good if you buy that book, right? It's very useful. Now, we talked about this yesterday, investigating the reaction of metals with dilute acids. And we talk about this again. We said about talk about the ability of a metal to ionize and to produce electrons, and then that electron gets picked up by the hydrogen ion there to produce hydrogen. So the faster metal produces the electrons, the quicker they are accepted by the hydrogen there, and the greater rate at which this hydrogen is produced. But this is a nice question. I'm giving you something called the ionization energy of these, okay? In electrode potential, the metal with the highest negative electrode potential is more reactive than those with a lower negative electron potential. In this case, the magnesium will be more reactive than that, which is their next negative. Aluminum is more than this. Zinc will be more reactive than iron, and see copper has a positive electrode potential there. So based on this, you can make a hypothesis, and then you can carry out your reaction using these. Carry out that. There's a procedure there. What you do, you get that sample of each of these, and you take test tube with acid, label test tube these 5 test tube with the same amount of acid of the same concentration at the same temperature, and then you pour all of these at the same time into each test tube with the acid, and you can absorb the rate at which hydrogen is produced, and you can rank your metals there. Based on that now, unfortunately you have to get that. You'll decide whether or not a reaction will take place here, and if it does, you'll have to balance the equation. Strips made of metals used in the question above have lost their labels. This table shows the results obtained when each of the strips were reacted separately with each of the following solutions. You're asked to identify the strips based on the observations made and the results obtained from the problem above. There's some other application questions that I've done here too. Like this, something is called the thermite process. This type of thermite process is made by mixing ferric oxide with powdered aluminum in a 3:1 ratio by mass. When you ignite that mixture, it can attain a temperature up to 4,500 degrees Fahrenheit. That's very, very high. And people will use this reaction here if they want to melt something very quickly, like you have the rails on the railway track is broken or something, and you want to weld it. The way that piece of thing is broken, they create this reaction. It heats up that metal to such a high temperature, and then you can quickly weld that thing. And this is how it happens here. Here's a mixture here. Here's a thermite here. You put a piece of magnesium strip there to ignite that, boom, and you get that hot flame coming out there. That's a thermite reaction, and it's a single displacement reaction. See reaction here, look. The aluminum is able to take away the oxygen from that. Something similar to that happens in the blast furnace. Blast furnace is used to extract iron from its ore, iron-3 oxide. So if you have if this is very, very hot and you react that with hot coke, carbon there is able to remove the oxygen here to give you carbon dioxide here. Another question is here too. You can read that. You can read that and try to do it. Okay? All the answers are given in the solution manual. Well, thank you for listening, and I hope that was useful to you.